A new kind of worm just crossed a threshold nobody thought we'd cross so soon. On October 17th and 18th, 2025, researchers uncovered GlassWorm, the first self-propagating worm targeting Visual Studio Code extensions distributed through the OpenVSX marketplace. This isn't a typical supply chain compromise. It's a worm that hides executable payloads inside invisible Unicode characters, uses public blockchain transactions as a stealthy command channel, and turns infected developer machines into remote-controlled proxy nodes and persistence platforms. In this episode, we'll unpack the full technical chain, how the invisible code is authored and executed, why the Solana blockchain and Google Calendar are being abused for C2, what the final payload, called Zombie, actually does inside infected hosts, and the exact detection, containment, and recovery steps security teams and developers need to execute immediately. If you build, publish, or run extensions or packages, this one is critical. Let's start with a short, concrete timeline and facts. On October 17, 2025, 7 OpenVSX extensions were found to contain invisible malicious code. By October 18, the campaign analysis was in full swing, and by October 19, researchers detected at least one infected extension in the Microsoft VS Code marketplace as well. Known installs at discovery time were approximately 35,800. Several extensions were still actively distributing malicious updates when researchers published their findings. This is significant for two linked reasons. First, it is self-propagating. The malware steals credentials and uses them to push malicious versions to additional packages and extensions. Second, the attack uses novel stealth techniques to defeat both human review and many automated scanners. When stealth and autonomous propagation combine, a supply chain compromise becomes a worm capable of exponential spread. To understand why GlassWorm matters, think about the chain of trust in modern software development. Contributors push code, maintainers review it, CI builds it, and users or other developers install artifacts. GlassWorm breaks that trust in two places. First, it hides malicious payloads from human reviewers and many static tools. Second, it weaponizes developer workstations, machines that typically hold tokens and privileged credentials, and uses them as stepping stones to expand infection. Once those privileged machines are compromised, containment becomes substantially harder because the infected hosts can reach internal systems, CI, and package registries that external attackers can't. The result is a worm that leverages both invisible code and privileged credentials to replicate by design rather than by human error alone. The most novel trick in GlassWorm is invisible, executable code hidden with special Unicode characters. Attackers embedded JavaScript using zero-width characters, variation selectors, and other non-printable Unicode code points that render as blank lines or whitespace in most editors, diffs, and web views. To a developer doing a normal code review, the file looks clean. To a static scanner that tokenizes visible text, it looks benign. But to a JavaScript parser configured to accept or normalize those code points, the sequences resolve into executable tokens. Practically, this means an attacker can place active code inside what appears to be empty space. A signature-based or visual inspection process won't find it. The code executes at runtime and can perform network calls, read local files, and harvest credentials. The key defensive lesson is simple but far-reaching. Visibility cannot be assumed. Tools and reviewers must normalize and flag non-printable Unicode, and CI must treat long runs of zero-width characters as high risk during pre-published checks. The campaign wasn't discovered because someone manually found invisible glyphs. It was discovered because the extension exhibited suspicious runtime behavior, network requests and credential access unrelated to its declared functionality. That triggered a risk engine alert for the CodeJoy extension when version 1.8.3 added unexpected behavior. Manual inspection of the visible source revealed nothing. The breakthrough came when researchers treated the empty lines as encoded data and extracted non-printable sequences from the file. After normalization and decoding, those zero-width sequences contained base 64 payloads in JavaScript. The payload unpacked into stages that connected to blockchain-encoded C2 and remote payload servers. So the practical investigative takeaway: when runtime behavior is suspicious, escalate to binary level and encoding level inspection. Normalize Unicode, extract zero-width runs and decode them. Treat empty space as potential data. The primary command and control channel used by GlassWorm is the Solana blockchain. The malware scans the Solana ledger for transactions originating from a hard-coded attacker wallet address, and inspects the memo field of matching transactions. Inside that memo is a small JSON object containing a base 64 encoded URL which points to the next stage payload. Why use blockchain? Because it is immutable, decentralized, and public. Once an attacker posts a memo, defenders can't delete it or force the blockchain to forget it. The attacker can continuously publish new memos with new payload URLs for virtually no cost. Additionally, looking up transactions or querying public RPC endpoints looks like normal blockchain activity and won't necessarily trigger traditional security alarms. Using Solana as a C2 channel creates an almost permanent, resilient message board for malware instructions, a permanent place to hide the next stage URL. Solana is the primary lane, but GlassWorm layers redundancy. The malware also consults a Google Calendar event where the event title contains another base64 encoded URL. Why a calendar? Because it's a legitimate cloud service that's rarely blocked outright and can be edited by anyone controlling the calendar event. The calendar acts like a low-profile, easily edited backup message board. In addition, the worm fetches encrypted payloads from direct IP endpoints, conventional HTTP hosts. These provide fast payload delivery when available. If those hosts are taken down, the blockchain memo or calendar event can point victims to a new host. This three-layer model, blockchain, direct server, calendar, is explicitly built to survive takedowns and operator interference. For defenders, the implication is that blocking one infrastructure component is insufficient. Attackers have engineered multiple fallback channels. When an infected client decodes a base64 URL from the blockchain memo or calendar, it issues an HTTP request to that URL. The response body is an encrypted payload. In the samples observed, AS256 CBC was used. Critically, the decryption key is provided dynamically in custom HTTP response headers. That design forces a defender to capture the exact request/response pair to decrypt payload content. Static archives of payload files without their live headers are useless for analysis. Operationally, this makes it harder to intercept and reverse engineer payloads from caches or mirrors. It also complicates offline scanning. Defenders must capture full header metadata or instrument live endpoints to collect keys. For incident response, this means network capture and live forensic evidence are essential for decrypting and understanding the payload. The decrypted final stage is called Zombie, a modular remote access Trojan and network toolkit. Zombie converts infected developer machines into active nodes for attacker operations. The capabilities observed include deploying a SOCKS proxy server to route attacker traffic through the victim's IP, installing hidden VNC servers, HVNC, to provide invisible remote desktop sessions, loading WebRTC modules for peer-to-peer control channels that bypass typical firewall restrictions, using BitTorrent DHT for decentralized command distribution, auto-restarting and persisting across reboots, loading additional modules on demand to extend functionality. Altogether, Zombie doesn't just steal data, it provides a platform for attackers to operate within victim networks, anonymize their traffic, pivot internally, and maintain control through decentralized delivery mechanisms. Let's unpack these capabilities more deeply. SOCKS proxy. Once Zombie opens a SOCKS listener, attackers can route scanning, exploitation, or command traffic through the victim's IP address. This obscures the attacker's origin and can bypass IP-based allow lists that trust internal addresses. WebRTC. WebRTC enables NAT traversal and direct peer connectivity using ICE, stun, and turn. Zombie's WebRTC modules allow direct, real-time control channels that are difficult to block because they look like legitimate browser media and data traffic. They can survive stringent perimeter security if stun/turn servers are reachable. BitTorrent DHT. Storing control data in the DHT decentralizes command distribution. Any node that queries the DHT for the attacker's key can retrieve commands, and there's no central server to seize. This makes the command plane resilient and politically difficult to disrupt. HVNC. Hidden VNC creates an invisible virtual desktop. From the attacker's perspective, they have full interactive control of the victim's environment without creating visible windows or obvious UI artifacts. That means they can use existing logged-in credentials, browser sessions, and internal tools to access systems without additional authentication barriers. The worm's self-replication cycle is straightforward but powerful. After execution, GlassWorm hunts for credentials, NPM tokens, GitHub personal access tokens, Git credentials stored by developer tools, OpenVSX published tokens, and even browser extension storage that might hold wallet seeds or private keys. Valid tokens are used to push malicious updates or publish compromised versions of packages and extensions. Each new compromised package or extension becomes a distribution vector. Because many developer environments auto-update extensions and packages, the worm can infect large numbers of developer machines with zero user action. That exponential infection model is what makes GlassWorm a true worm. Each infected host can generate more infected hosts autonomously. Who should be alarmed right now? First, extension authors and package maintainers. If you publish to OpenVSX, NPM, or the VS Code marketplace, your accounts and published tokens are directly at risk. Second, any developer machine that stores publishing tokens, CI secrets, or SSH keys is at risk. Third, enterprises with developer endpoints inside corporate networks face a pivot risk. An infected developer machine can be used to reach internal services, CI pipelines, and production systems. At the time of discovery, the observed impact included about 35,800 installs and active payload infrastructure. The malware targets roughly 49 wallet extensions among other artifacts, meaning direct financial theft is a real outcome. The combination of automated distribution and stealthy persistence makes the attacker capable of both theft and long-term lateral movement inside networks. If you're responsible for developer security or maintain packages, take these immediate steps. 1. Inventory and block known infected package names and specific versions. Use endpoint management to uninstall or block those versions. 2. Rotate exposed tokens. Revoke and reissue NPM tokens, GitHub PATs, OpenVSX published tokens, and SSH keys that may have been used on infected hosts. 3. Revoke tokens at the source. Revoke from the registry UI or API and regenerate fresh credentials. 4. Isolate suspected hosts. Take compromised hosts off the network and gather forensic artifacts. Memory dumps, process lists, disk images, and network captures. 5. Hunt for proxy listeners and unexpected services on developer endpoints. Scan for unknown processes listening on typical proxy ports or binding to suspicious interfaces. 6. Search telemetry for requests to Solana RPC nodes, unusual Google Calendar lookups, and outbound connections to the identified IPs or domains. 7. Block known C2 IPs and domains at the egress firewall and add them to internal block lists. 8. Treat infected hosts as catastrophically compromised. Rebuild from known good images once artifacts are collected. Follow the pattern. Identify, isolate, rotate, rebuild, review. Assume credentials were exfiltrated. Quick favor: if this breakdown was useful, like the video, subscribe to Infosec now, and share it with a colleague who manages developer security. A quick thumbs up and a subscription help YouTube recommend these threat alerts to teams who actually need them. Thanks. Back to the technical guidance. Concrete forensic indicators to hunt for include files containing long runs of zero width or variation selector Unicode characters in JavaScript or extension files. Flag any file with excessive non-printable characters. Processes making RPC calls to Solana endpoints or unusual HTTP requests that include base64 encoded payloads. Outbound connections to suspicious IPs serving encrypted payloads and to known exfiltration servers. Unexpected listeners on developer machines, SOCs or proxies that shouldn't exist. Signs of headless VNC or virtual desktop sessions running under unusual service names. WebRTC signaling or stun/turn traffic originating from developer endpoints outside normal browser activity. When you find suspicious files, extract raw bytes, normalize Unicode, and decode zero-width sequences to reveal embedded base64 or JSON. That will often expose the hidden payload strings. If you confirm an infection, the safest path is containment and rebuild. Containment. Isolate affected hosts immediately. Collect forensic artifacts, memory, disk images, process lists, and network captures. Recovery. Reimage developer machines from known good air-gapped images. Do not rely on in-place cleaning because persistence mechanisms may survive. Reinstall tools from verified sources and pin versions. Regenerate and rotate all secrets and tokens after systems are rebuilt. Post-recovery. Rotate CI tokens, reissue code signing keys, and require fresh authentication for automation pipelines. Review audit trails for where stolen credentials were used to push code or create new packages and coordinate remediation with registry providers. Notify downstream consumers so they can take defensive action. Remember, assume exfiltration occurred and rotate everything that might have been exposed. Short-term controls you can implement immediately. Enforce least privilege for package published tokens and require fine-grained scopes. Use hardware-backed MFA and short-lived credentials for publishing operations. Disable auto-update of critical extensions in corporate developer images or pin versions centrally. Add CI pre-published checks that flag 0 with Unicode and base 64 blobs and source files. Deploy EDR rules that detect new persistent listeners, unknown SOX proxies, or modules spawning hidden VNC servers. Restrict egress from developer machines to a limited set of allowed destinations and protocols. Monitor for Solana RPC traffic and suspicious calendar lookups in your network telemetry. These steps raise the cost and complexity for attackers trying to replicate and propagate automatically. GlassWorm shows systemic changes are needed. Marketplace and registry providers should normalize and disallow non-printable and zero-width Unicode sequences by default. Code review tooling should highlight invisible characters and force explicit approval for files containing them. Registries should make it easier to expire and rotate published tokens and require multi-party approval for wide-reaching updates. Emphasize cryptographic provenance. Signed packages and reproducible builds to ensure artifacts match trusted sources. Organizations must treat developer endpoints as production-class assets with monitoring, network controls, and token hygiene. These are not small changes, but they are necessary to make the next wave of supply chain worms far less likely. Use this practical Week 1 checklist. Pin critical dependencies in developer images and disallow auto-update for images used in production. Rotate all published tokens and move to short-lived tokens where possible. Add pre-publish hooks that reject files containing long runs of non-printable characters or unexpected base 64 blobs. Require signed commits and multi-person approvals for publishes to packages with a large install base. Run both source and binary scanning on every publish artifact and compare results to historical baselines. Maintain a corporate whitelist of approved extensions and enforce it with group policy. Following these steps will materially reduce risk and limit the worm's ability to spread through automation. Communication reduces confusion during incidents. Security teams should provide clear, step-by-step remediation instructions, which extensions to remove, how to rotate tokens, and how to collect forensic data. Explain temporary policy changes, like disabling auto-updates, and why they are necessary. Offer a remediation playbook, who to contact, how to escalate, and what logs to capture. Coordinate with registry operators and marketplace providers to block malicious versions and publish advisory guidance. Clear, practical instructions speed recovery and reduce the risk of accidental re-exposure. GlassWorm is a structural shift in supply chain threat models. Attackers combined invisible code, decentralized C2 channels, and privileged developer tokens into a resilient self-propagating worm. That combination turns single package compromises into potentially exponential epidemics. Key takeaways. Treat developer tokens and environments as high-value assets. Normalize and detect zero-width and non-printable Unicode in CI and pre-published checks. Enforce least privilege, short-lived credentials, and hardware MFA for publishing. Apply egress filtering and behavioral detection on developer endpoints. Reimage compromised hosts and assume credentials were exfiltrated. Start with a token audit and updated incident playbooks. Those two actions alone will materially reduce your exposure to worms like GlassWorm. This campaign should be sobering but not fatalistic. Each major attack pushes defenders to evolve. GlassWorm combined techniques we've seen in isolation into a resilient, stealthy package. And that means defenders must combine build time checks, runtime monitoring, and strict token hygiene. If you manage packages or developer environments, treat those environments as production assets. Normalize Unicode detection in your tool chain, rotate tokens, and add egress controls. The cost of inaction is now visible. A worm that can hide in plain sight and use your own machines as infrastructure. Subscribe to Infosec now for more deep technical breakdowns and practical, actionable guidance on defending modern developer ecosystems. Stay safe out there.